activity. If we observe these areas in polarized light, we can obtain magnetograms as the one shown here. In this magnetogram, black and white areas represent the opposite polarities of the line-of-sight magnetic fields. Of course, active regions are related with the largest magnetic flux concentrations. The areas that we find outside these active regions are known for historical reasons as the quiet sun. We can already observe at this medium spatial resolution that in the quiet sun we have also small-scale magnetic structures. The distribution of these magnetic features shows a reticular pattern, and for this reason, these structures are known as network magnetic fields. If we observe the quiet sun with an even higher spatial resolution, at visible light we can already observe the solar granulation. This pattern is produced by the convective processes that take place in the solar surface. If we observe the same areas in polarized light, the magnetogram shows that outside the largest network magnetic structures, the quiet sun is fully magnetized. In particular, we observe many small-scale structures everywhere in the quiet sun. These small magnetic elements are known as internetwork magnetic features. The evolution of quiet sun magnetic fields is completely dominated by convective motions. In particular, it is well known that network magnetic elements are seen to concentrate at the boundaries of supergranular cells. In this movie of the solar granulation, we cannot directly observe a supergranular cell, as the supergranulation takes place in deeper layers in the sun. However, from these movies, we can infer the proper motions of granules, and in this way, infer the horizontal velocities of supergranules. So, just tracking the proper motions of these granules, we can obtain horizontal velocity maps as the one shown here. In this horizontal velocity map, we can clearly observe one of those supergranular cells, where the flows move from the interior of the cell towards the boundaries. In these boundaries is precisely where network magnetic elements are seen to concentrate. Internetwork magnetic elements are also seen to be affected by these flows. In particular, they are seen to move from the interior of the cell towards the boundaries following these flows. In this way, they can reach the network and replace the entire network flux in more or less one day. Okay. If we observe internetwork areas with the highest spatial resolution that we can currently achieve, we see that internetwork also shows a reticular pattern, in this case at mesogranular scales. Mesogranulation is a medium scale between supergranulation and granulation. Here I show one of those mesogranular cells. In particular, I show the horizontal velocity map and the related magnetogram. In the magnetogram, we can see that the structures are mostly located within the periphery of this mesogranular cell. Indeed, using this IMAX data, Yel Xiaoxue and co-workers found that roughly the 85% of the pixels with longitudinal magnetic field above 100 Gauss are located at the boundaries of such mesogranular cells. Even at smaller scales, at granular scales, in the quiet sun, it has been observed that the flux emerged to the solar surface in the form of small-scale magnetic loops. Here I show an example of one of those small magnetic loops. In particular, I show the intensity map, the magnetogram, the linear polarization, and the line-of-sight velocity map. In the magnetogram, we have two opposite polarity patches. And in the linear polarization map, we have one patch. The linear polarization signal gives us information of the transversal component of the magnetic field. So the fact that this signal, here shown by the white contour, is located between the two opposite polarities, here shown by red and green contours, suggests that what we have here is just a small-scale loop-like feature. As we can see in the intensity map, this structure is located within a granule. This means that it is located within plasma that is coming to the solar surface. This plasma, the upflows, can be observed in the line of sight velocity. Here, blue areas represent plasma coming to the solar surface, upflows, and red areas, downflows. So we can say that this small-scale loop-like feature is emerging to the solar surface. Simulations of the solar surface convection also displays highly localized sinks where cool plasma returns to the solar interior. Because of the conservation of the angular momentum, a vortex can be formed as the plasma approaches to this downdraft. Indeed, vortex flows are quite common in simulation. Here I show an example of one of those simulations. In particular, I show the continuum intensity map, where we can see 3 different vortex-like features. Here I also show the velocity vector of one of those vortex-like features. In particular, a black arrow shows the horizontal component of the velocity, and in colors we show the line of sight velocity. In red we have downflows, and in blue we have upflows. So we can see that within this vortex feature we have a localized downflow. Okay. Due to the small size of vortex flows, they have remained elusive to solar observations during a long time. They have been only recently observed using the newest solar telescopes. In particular, Bonnet and coworkers were the first detecting them. They did it just following the trajectories of bright points. Bright points, as I show here, are just the photometric counterparts of magnetic elements. So they found that the trajectories of bright points shows logarithmic spirals as they approach to a common converging point. Later, the same authors found that this kind of vortex flows can be also detected at magnetograms. Here I show an example of one of those vortices that we can also see in this magnetogram. We can check that this structure is rotating. This kind of vortex can be also observed at the continuum intensity image, and of course, in the related horizontal velocity maps. Such an observation may suggest that localized sinks are locations where the magnetic fields can concentrate. However, in order to see if there is such a relation between sinks and magnetic fields, still an statistical information is required. In order to study the relation between sinks and magnetic fields, we need high spatial resolution and high polarimetric sensitivity. Such an observations has been recently achieved using the IMAX instrument. IMAX is a spectropolarimeter, an imaging spectropolarimeter, which flew on board the Sunrise Balloon Solar Observatory. Sunrise was above 40 kilometers above the Earth's surface. So being at this height, IMAX provides nearly same-free time series with a cadence of 33 seconds, which is fast enough to study the evolution of quasi-magnetic fields. IMAX also provides the full Stokes vector from which we can infer the different physical parameters of the solar atmosphere. For doing that, we use inversion codes. In particular, we use the SIR code. And we can obtain parameters such as the line of sight velocity. Here I show the line of sight velocity over the field of view of IMAX, where we can see that the granules are seen in blue as they are related with outflows, and the intergranules are seen in red as they are related with downflows. We can also infer the inclination of the magnetic field lines in the different structures, its field strength, and for those two parameters, we can also build longitudinal magnetograms as the one that I show here. We also use local correlation tracking techniques to infer the proper motions of granules. In this way, we can obtain the horizontal velocity maps. And from these velocity maps, we can also compute the divergency and the vertical vorticity. In this image, in colors, I show the divergency, and in white, with white arrows, I show the horizontal velocities. All over IMAX field of view, we find that the field of view is full of mesogranular scale cells. If I zoom in one of those cells, we can see that within the granule, we have positive divergences. And as we approach to its boundaries, as the flows converge into the boundaries, we have negative divergences. Okay. Now, first, we want to somehow identify those boundaries. In order to do that, we use cork movies. So we put one cork at one virtual cork at each pixel, and we let them to be advected by these horizontal flows. If we do that, after some 20 minutes, we find that we have a fully developed network at mesogranular scales. This happens as the cores are advected by these granular flows and are concentrated at the boundaries of these cells. In this way, we can identify the mesogranular lanes, also called mesolanes for short. We do that for 2 different time series of 22 minutes each, and we define mesolanes as those locations where we have at least 2 cores and 1 pixel neighborhoods. Now, if we let the cores to be advected even for longer times, we find that finally end up in well-localized places, where the horizontal flows converge towards a common point. In this way, we can also identify the inflow centers. Once we know the position of these inflow centers, we define converging flows as 360 kilometers radius circles around these centers. Here, I show these converging flows with red circles in the image. Okay, so we identify 131 converging flows within both observed areas, and we identified 2 different types of converging flows. Some of them shows radially converging flows. We call them sync flows, and others display vortex-like motions. We find that 60% are sync flows, and the other 35% are vortex flows. In order to characterize these 2 types of converging flows, here I show the histograms for the vertical vorticity at sync flows and at vortex flows. We can observe that at sync flows are characterized by having very low vorticities, as the histograms peaks at 0 values. On the other hand, the histograms for vortex flows shows 2 different groups. Some of them have negative vorticities and other positive vorticities. The ones with negative vorticities are related with vortex flows that they are rotating in the clockwise sense of rotation, and the others are rotating in the counterclockwise sense of rotation. We find more or less the same amount of clockwise and counterclockwise vortex flows. In previous works, they have been talking about sinks, even without showing if these converging flows have something to do with downflows. However, here with IMAX, we have also information of the line of sight velocity. So we can check if these converging flows are related with downflows or not. Here, in these 2 maps, I show the mean line of sight velocities as an average over the whole time series. This is for time series, the first time series, and this is for the second one. In the image, I also show in green the mesogranular lanes. Here, I display the histograms of the line of sight velocities for different regions. In black, I show the histograms all over the field of view of IMAX. In green, I show histograms only within mesolanes. And in blue, I show histograms within mesogranules. Here, we define mesogranules as those areas outside mesolanes. So, and then here the vertical dashed line shows the median values of the different distributions. We can see that mesogranules are slightly blue shifted. They are related with outflows, while mesolanes are red shifted. So we can say that mesolanes are mostly located in downflow areas. Now we can do the same for converging flows. Here I show the position of converging flows using these red circles. As we can see, the distribution of this converging flow is a mesogranular distribution, as they appear at the vertices of these mesogranular lanes. If we plot the histogram within these converging flows, we find that this histogram is also redshifted, and even with stronger downflows than in mesolanes. So from here, we can conclude that mesolanes, and in particular converging flows, are related with persistent downflows. So from now, we can refer to converging flows just as sinks. Okay, now we want to check the relation between sinks and magnetic fields. Here I show two different snapshots at the different time series of the magnetograms. If I plot here the mesolanes, we can see that almost all the magnetic structures are located within mesolanes. In order to quantify this, for each threshold value in this axis, we consider the set of pixels above each threshold, and we compute the fraction of this set at the different places. For example, at mesolanes, here in green, or at mesogranules, in blue. So, in particular, for a threshold of 100 Gauss, we have that the 80% of the pixels above this threshold are located at mesolanes, and only the 20% of these pixels above 100 Gauss are located at mesogranules. So almost all the magnetic fields that have these values above 100 Gauss are located at mesolanes. This was already found by Gels, Chaussee, and coworkers in a previous work. But now we have also information of sinks. So we want to check what happens with sinks. If we do the same for sinks, we find that a large amount of the strongest magnetic fields are located in these areas. In particular, for a threshold of 500 Gauss, we find that the 40% of the pixels above this threshold are located at sinks. This large amount of magnetic fields at sinks are even more impressive if we take into account that sinks only covers the 3% of the full field of view, while mesolanes covers the 20% of the field of view. So from here we conclude that the strongest magnetic fields are preferentially located at sinks. Okay, we have seen that the strongest magnetic fields are at sinks. Now we want to check what happens with the weak, small, loop-like features. In these two observed areas, Martinez, Gonzalez, and coworkers detected all the loop-like features. The position is here shown by black dots. We find that roughly the 70% of the loops are located at mesogranules, the 30% at mesolanes, and only the 5% at sinks. These fractions are almost of the same order of the surface fraction that covers the different areas. So we conclude that the small-scale loops do not show any preferential distribution at mesogranular scales, as they do the strongest magnetic elements. Okay, we have seen that the strongest magnetic elements are located at sinks. Now we want to study how these strong magnetic fields are formed in these areas. In particular, I'm going to focus in this magnetic element, and I'm going to study the formation of these structures. Here I show the time sequence for the continuum intensity the line of sight velocity, and the magnetogram. The red and blue contours shows the opposite polarities of the magnetic fields, as you can see in the magnetograms. And the blue contours shows the linear polarization signal. So what we have here is just a small scale magnetic loop that is emerging to the solar surface. If we continue its evolution, we find that as it emerges, the negative foot point here in blue cancels out with this opposite polarity patch, while the positive patch survives to this interaction. Then this positive patch is advected by the horizontal motions, in particular is advected towards the center of this sink, together with other same polarity patches. In this way, these polarity patches merge and form a stronger magnetic element at the center of this sink. In this way, the field strength increases from 300 Gauss to 600 Gauss. Once we have our magnetic element, we can continue with its evolution. In this case here, I show the field strength intensity. And we find that later, the downflows starts to increase within the magnetic element. And the field strength increases. Here, what we have is just an intensification phase of this magnetic element. During this intensification, we also observe the formation of a small bright point. If we study what's happened to the surrounding granules, we find that these granules are converging towards the magnetic element, as they are located in a persistent sink. So if we put the movie, we can see how these granules elongate and converge toward the structure as the magnetic element intensifies. So it seems that this intensification process is somehow produced by the compression of these granules. Here I show the evolution of the different parameters within the magnetic element. In particular, in red, I show the field strength, and in black, the line of sight velocity. And we find that the field strength increases from 600 Gauss to 1,600 Gauss. Meanwhile, the downflow also increases from 1 to 1.5 kilometers per second. Then we can continue with the evolution of these magnetic elements. And we find that the field strength decreases and then intensifies again. This can be also observed in the evolution of the field strength here. When the field strength decreases, the line of sight velocity the downflow decreases. We reach almost zero values, and then during the second intensification phase, again, the downflow increases. So, as a summary of the formation of this magnetic element, we can say that the formation starts with the emergency process of a small scale loop. Then one of the foot points is advected towards this sink together with other same polarity patches. In this way, they merge and form a stronger magnetic element, and then this element is compressed by surrounding granules and intensifies up to kilogauss values, and then we start to observe what can be maybe a subsequent oscillatory behavior. However, here we only observe one period of this possible oscillatory behavior. However, in other magnetic features, we find that this oscillation can be observed during at least 20 minutes. In particular, we find what we call multi-core magnetic structures. These magnetic structures are related with they are seen as structures that they have more than one inner core. Here I show, for example, the time sequence for one of those multi-core structures. This is the line of sight magnetic field, and here I show the CM band filtegram. In this panel in the right, I also show in colors the line of sight velocity, and in arrows shows the horizontal velocities, where we can see that what we have here is just a vortex flow. So this element is located within this vortex flow. We see that at the beginning, we have two inner cores. These cores are quite small, and we cannot resolve them. However, we know that they are indeed real, as they appear related with two different bright points. When the cores merge, they form a stronger magnetic element. And then they split again into two different cores. So during the coalescence process, we observe an intensification, and when it splits again, the structure decreases the magnetic field strength. So this process can take place during the whole evolution, and this gives rise to magnetic field oscillation of the global entity. Indeed, we find that multi-core magnetic structures are quite common in our observations. In particular, in this time series, we find 28 examples of multi-core magnetic structures. Here I show them using these black boxes. Here I show also one snapshot of each of those 28 multi-core structures. In particular, I show the longitudinal component of the magnetic field, where we can check that they are indeed related with at least 2 inner cores. Are in the mesogranular lanes, yeah. Yeah. No, I'm not seeing here the supergranulation. We are mostly located at intergranular lanes, internetwork areas. Now we are going to focus in the evolution of one of those multi-core structures. In particular, we are going to see the interaction with surrounding granules. Notice that this multi-core structure is located at this sink. So, as it is located in a sink, there we have granules that they are converging towards the structure all the time. So these converging granules are somehow buffeting the structure. So the continuous fragmentation and coalescence process are produced by this buffeting. In order to see these convergence processes of granules, we can see them in this movie. Also in the continuum intensity, we can see how these granules are converging all the time towards the structure, and they are buffeting the magnetic structure. When the structure is compressed between 2 granules, we see fragmentation processes. However, as soon as a fragmentation process takes place, the converging flows of the sink take the different cores and they merge them again. Here I show the evolution of 2 different inner cores, in particular the evolution of the field strength. In green, we are following one of the inner cores, and in red, another core. And here I show one of those coalescence processes. Here, when the 2 cores merge, I show only one line, black line, as we have just one magnetic element after the coalescence process. We can see that during the merging, the field strength intensifies, and then it splits again into 2 different cores. During the splitting, the field strength decreases. So as I said before, this continuous fragmentation and coalescence process gives rise to magnetic field oscillation of the global entity. Such an oscillation has been previously observed by Martinez Gonzalez and co-workers in other 4 magnetic elements. Here I show an example of 2 of them, and here I show the magnetic field oscillations. In that work, they suggest 2 possible scenarios. One possibility is that these oscillations are produced by characteristic oscillation modes of isolated flux tube. And another possibility was that they are may produced due to the forcing by granular motions. Now we wonder if these structures have something to do with multi-core structures, because if they are related with multi-core structures, then we will support the second scenario, as we have seen that these multi-core structures are continuously being buffeted by surrounding granules. So we analyze the 4 structures again, and here I show the evolution of those 4 magnetic elements. In particular, I show the line-of-sight magnetic field component. And we find that they are indeed multi-core magnetic structures. So we conclude that that oscillations were also produced by the granular buffeting. Okay, so as a summary, we can say that thanks to the high spatial resolution and polarimetric sensitivity of IMAS, we have been able to study the relation between sinks and magnetic fields in the quiet sun. We have found that sinks are related with converging horizontal velocity flows and persistent downdrafts. We have found that the strongest magnetic fields are located at these sinks areas. In particular, the 40% of the pixels with longitudinal component of the magnetic field higher than 500 Gauss are found in these areas. And finally, we have studied different samples where we have seen that the sinks can play an important role in the formation and evolution of quasi-magnetic features. Thank you.
Thank you, Iker. Questions?
Iker, I have a question concerning the vorticity, the vortex flows that you showed toward the beginning of your lecture. Maybe you could show the corresponding slide?
Observations or simulations?
The observations. The histogram. You showed a histogram separating cases.
Histograms in the line of sight velocities.
The ones before about the vorticity.
Okay.
That one, exactly. So just for my understanding, so how do you measure the vorticity?
From the horizontal velocities.
Which is determined via LCT, I suppose, local correlation tracking.
Yes.
Okay, so the question is, the vorticity is a measure of the derivatives of the velocity field. And so you can have high vorticity because you have a vortex flow, like the intuitive vision that everyone has, or because you have a shear flow.
Yeah, sure.
And so along mesogranular lanes, you might have shear flow. So how do you distinguish in this case between the two possibilities?
I cannot have shear flows because my converging flows are related with where the corks end up. So the corks end up there because they are at the central position of inflow centers. I don't know if I can explain. For example, here, the corks end up in these locations because we have converging flows. So if we have a shear, then the corks end up somewhere else. I don't know if I explained.
So you select those cases in which you have the converging flows, and there you measure the vorticity and make this histogram.
Yes,
okay.
The histograms are coming from the central position of these converging flows. I only get the histograms from the points where the corks end up in my cork movies.
Thank you.
Iker, one question. Inside the mesogranular network, inside, we have granules and intergranules.
Yes.
What do you see there, and especially in the intergranules, where we know also that we have downflows there?
From the observational point of view, mesogranules are seen as exploding granules. When you have an exploding granule, those positive divergences that we observe within the mesogranules are produced by exploding granules. Exploding granules are everywhere, and the locations where we have exploding granules usually shows that they repeat once and again. So what we have there is, they call them trees of exploding granules. So they remain there during long times, and it's why the mesogranules live for some hours. So what we observe there inside mesogranules, yes. Yes. The strongest magnetic structures are at the boundaries of mesogranular lanes. This is clear, no? So, for example, here I show one of those mesogranules, and here I show the time sequence of the continuum intensity. What we observe inside this mesogranule is that we have different exploding granules. Here I show, for example, with the arrow, one of those exploding granules. Here, this granule shows a darkening in the interior, and after some time, we see that it fragments in many different granules. So these fragments are moving towards the boundaries of the mesogranular lanes. And when we use local coloration tracking, we are tracking the proper motion of these granules. And it's why we observe these positive divergences there. Yes. Yes. Okay. We find that the strongest magnetic elements are at mesolanes. But we find that loop-like features, which are weaker, they don't show any distribution at mesogranular scales because they are related, they appear at granular scales. They emerge to the solar surface at granules. So indeed, we find that loops can appear inside mesogranules. In this case, we have detected two loop-like features within the mesogranule. I didn't show it this, but... And then we track the evolution of the foot points of these loops. Here I show in contours the loops, the foot points of these loops. And we find that they are spurred by exploding granules towards the boundary of the mesogranular cell. Here I show the trajectories of the foot points of these loops. And we can see that the trajectory shows that they are being advected towards the boundaries of the mesogranular cells by these flows.
Excuse me. I have a question concerning these loops, these little loops that appear
Yes.
in granules. So from your statistical measurements, do you find any hint that some of those may appear repeatedly, in the sense that you find these loop appearances in certain regions time and time again, or are they really at random?
The location of loops are coming from a work by Maria Martinez Gonzalez in 2012. And in that work, they found that, indeed, there are locations where there are many loops appearing. So,
repeatedly in time. So,
yes.
so there appears a loop, and
Yes.
then later on another,
Yes.
another. Okay.
but then when I put them in my maps of the mesogranules, I find that they don't show any distribution, peculiar distribution at mesogranular scales, at least.
Mm-hmm. Okay. Thank you.
It seems that Fernando and I are occupying the whole questions and answers session. Sorry about that. One question concerning the kilogauss fields that, or close to kilogauss fields that you detect.
Yes.
If you go to the internetwork and you have the field of view of your internetwork, have you estimated the fraction of the field of view that it is covered by kilogauss field strengths?
Yes. So here, I have two magnetograms for two different time series. In this time series, I have computed the locations of mesogranular lanes. Okay? So here we have a lot of structures, and now if I put the mesolanes within these magnetograms, we can see that these mesolanes are indeed above these magnetic structures. So at least the largest and the strongest magnetic structures are seen to be located within mesolense. This is clear. Okay, now in this plot, I show here we have a threshold value, okay? So for each threshold value, let's say 500 Gauss, 1000 Gauss is here. Okay, but let's say 500 Gauss, okay? So I I take this threshold, and then I take the set of pixels in my field of view with values above this threshold, and I compute the fraction of this set of pixels in mesolense, in blue, in green, and in mesogranules. And I find that most of them, the 80%, are in mesolense. Okay? This means values above this threshold. There, they are also the ones with kilogauss values inside these statistics. This value increases with field strength. If we go to 100 Gauss, we see that almost all the pixels with values about 1000 Gauss are located at mesolense. Okay? And in sinks, it's the same. As we go to higher field strength, these values of magnetic fields at sinks increases. Okay, so in sinks, magnetic fields with 100 Gauss or larger are 1000. Sorry, I was confused. Yeah, 1000 Gauss here is in kilogauss. Okay, so here 1 kilogauss. So roughly the 70% are at sinks, and almost the more than 90% are at mesolense. Okay. How many pixels are? Okay. They are not a lot. After 500 Gauss, the number of pixels decreases a lot. Yeah. It's wild. Yes. I had somewhere the histograms of the... Sorry.
I have a much more naive question regarding these vortex-like structures.
Yes.
So for how long they can survive, how stable they are?
Okay, our time series are of about 20 minutes. So they live 20 minutes, but I guess that they can live even for longer because they appear at the boundaries of mesogranules. They are related with the flows that they came from mesogranules, and it has been observed that mesogranules can live some hours. So I will say that probably they will live for longer.
I just wanted to know, since the lifetime of these three different features is different, like you said,
Three different features?
the mesogranular
okay.
and the others, you just said that the sinks can survive for about 11 minutes, 20 minutes, you said
20
something
minutes
like
at
that.
least.
But the other features have different lifetimes. So I'm just wondering how you can compare the magnetic field of these three different features when they have this different lifetime. Because the evolution for every feature would be different. The magnetic field would be different during the evolution, right?
I was indeed telling to him that the lifetime can be, I think that they can be the same in mesogranous, mesolanes, and sinks, because they are all of them related. They are coming from the same flows. So I will say that the lifetime are the same.
Thank you, Iker. So I think we can thank you again. And see you at the scientific coffee in the cafeteria. Next week, scientific coffee will be again in the library. Bye. Thank you.